AP Pre-Calc. These are going to be section 1.9 and 1.10 notes on vertical asymptotes and wholes of rational functions. And our learning target is I can identify vertical asymptotes and wholes of rational functions. So if you remember from our last two sets of notes, a rational function is just the quotient or ratio of any two polynomials. And we normally write it as f of x divided by g of x, where f and g are your polynomials. And since we are dividing by a polynomial and have a variable in the denominator, rational functions have restrictions on their domain, meaning there are values of x we have to leave out. And that is because we cannot divide by 0. So any values where our denominator equals 0 has to be restricted from the domain. And these values, whatever makes our denominator 0, will be either a vertical asymptote or a whole in our graph. So both of those occur when our denominator equals 0. So let's look at when we have a whole versus when we have an asymptote. So a whole occurs when we have a common factor that cancels out. So essentially, I can get rid of this x minus 1 for f of x, which then creates a whole in my function, and we have a whole in the graph at x equals 1. Same thing for g of x, because we have x minus 1 in the numerator and denominator, and there are more of them in the numerator, g of x also has a whole at x equals 1. And you can see the graph, how a graph will have a whole. It'll be just an open circle, meaning that is not included in our domain. And then when we are looking at limits, so we can do left-sided limits and right-sided limits. So this is the limit as x approaches 1 from the left. That's what the negative sign as an exponent means. And then with the positive as an exponent, that's from the right. So as we approach from the left, we can see that we are approaching our whole, which has a y value of 3. Same thing as we approach from the right side. So that is why our limit equals 3. So our limit will always equal a number when we have a whole. On the flip side, we have a vertical asymptote when our factor in the denominator cannot cancel out. So we are left with, say, an x minus 1 in our denominator, because we can cancel this guy out, but there's still 1 left in the denominator. So both of those functions have a vertical asymptote at 1. And the way you know you have a vertical asymptote is you will see a dashed line that your function will never touch and never cross. And when we are looking at limits as we approach an asymptote, your limit will always be negative or positive infinity. So this one, as x approaches 1 from the left, y approaches negative infinity or goes down. And then on the right side, because the right side of our graph as we approach 1 from the right is going up, that limit is positive infinity. So with vertical asymptotes, our limit will always equal one of our infinities. So it'll equal a number if we have a whole there, positive or negative infinity. if we have a vertical asymptote. So now we have some examples, and we're asked to determine the x values of any holes or vertical asymptotes. So remember, a hole occurs if that factor appears in the numerator and denominator, like x plus 3. So because of that, we have a hole at x equals -3. And when I simplify that function, I get x minus 2 over x minus 5. And if I think about substituting 3 in there, so 3 minus 2 would be 1, 3 minus 5 would be -2, so we would be at -1/2. So our hole in our graph, or our open circle, similar to this guy from our previous example, would be at -3, -1/2. So you identify where your hole is, that x value, simplify your rational function, and then put the number from your hole into that function. Oh, and I put +3, not -3. So if we put -3, -3 minus 2 would be -5. -3 minus 5 would be -8. So that would be a +5/8 would be where our hole is. So then, remaining in our denominator is our x minus 5, which gives us our vertical asymptote. So that's where our hole and our asymptote is at. So our next example for B, we can see we have 2 x minus 2's in our function. So if we think about simplifying that, we have x plus 1 still on top, and we're left with 1 of the x minus 2's. And then in our denominator, we have the x plus 1 squared. But then once again, one of those will cancel with our x plus 1 from the numerator. So we're left with x minus 2 over x plus 1. So because we were able to cancel out x minus 2 and it's still in the numerator, that is where our hole is at. And then if we put 2 into the function, 2 minus 2 is 0, and then 0 divided by 3 would be 0, so it's at 2, 0 is our hole. And then because our x plus 1's canceled out, but there is still an x plus 1 in the denominator, we have our vertical asymptote at x equals -1. So because we still have our x plus 1 there, even though one of them canceled out, and we still have our x minus 2 in the numerator, that is why we only have one hole and one vertical asymptote. So part C, before we can identify our holes and asymptotes, we have to factor. We always want to factor first when identifying almost any one of our key features. So when I factor this guy, I have a common factor of x in our denominator, so I can greatest common factor in x, which leaves me with x squared plus 4. And because that is a sum of squares, I cannot factor that any further. So I do not have any holes because there's nothing I can cancel out. And then the x squared plus 4 will never be negative, so that does not give me a domain restriction. The x by itself does. It gives me a vertical asymptote at x equals 0. So next up, we're going to write limit statements as x approaches 2 for each of the following functions. So we're going to go 2 from the left and 2 from the right. And remember, if it is a whole, our limit equals a number. If it is a vertical asymptote, then our limit is positive or negative infinity. So, for the part A, or example A, our limit of f of x as x approaches 2 from the left, so we need our little negative exponent. And then if we look at our function to figure out what's going on at 2, we can see that we have a factor of x minus 2 in the denominator only, meaning we have a vertical asymptote. And to figure out whether it's going to positive or negative infinity, we want to think about just a simple sign chart. So looking at 2, what's happening on the right and the left? So if we think about substituting 0 in, so 0 minus 1 is a negative number, 0 plus 3 is positive, 0 minus 2 is negative. And because I have 2 negatives, that left side is going to end up being positive. Then on the right side of 2, I can check like 5. 5 minus 1 is going to be positive, 5 plus 3 is positive, 5 minus 2 is positive. So because we have all positives, we're looking at a positive number. Or sorry guys, I misspoke. We have to check numbers really close to 2. That's why I'm off. So we want to check like 1.5 and 2.5 to see really close to that vertical asymptote. Are we going up or down? So if we check 1.5, 1.5 minus 1 will be a positive number. 1.5 plus 3 is positive. 1.5 minus 2 is negative. So the left side is negative, which means our left limit is going to negative infinity. And then the right side, if we check 2.5, so 2.5 minus 1 is going to be a positive number. 2.5 plus 3 is positive. 2.5 minus 2 is positive. So our right side is going up, meaning our right limit of f of x as x approaches 2 from the right is positive infinity. So next, part B. So remember, we're still looking at our limits as x approaches 2 from the left, and the limit as x approaches 2 from the right. In this case, our function is g of x. So we want to see what is happening at 2. And because we can see x minus 2 in our numerator and denominator, and only 1 in both, we have a whole. So because we have a whole at 2, we want to think about if we cancel those out, leaving us with x plus 4 over x minus 3, when I substitute in my value for the whole, or 2, what do I get? So 2 plus 4 is 6. 2 minus 3 is -1. 6 divided by -1 means my whole is at -6. So the limit of g of x as x approaches 2 from the left and the right is going to be -6. And then I want you guys to try part C and see if you can figure out your left and right limits as x approaches 2. So be careful, make sure you correctly identify if it's a whole or a vertical asymptote. So up next, we are being asked to write an equation of a rational function with the following limit properties. And we're given 4 different limits. So if you remember from earlier, when our limit equals a number, that means we have a whole. So our whole will be at x equals 3, because that is what our limit is approaching. Meaning we need an x minus 3 in our numerator and denominator. And then our next limit, because they are equal to our infinities, we know this is a vertical asymptote. So we know we have a vertical asymptote at x equals 1, which means we need x minus 1 in the denominator only. So then we could write our rational function. So we need our whole on top and bottom. And then we need our vertical asymptote in the denominator only. So, part B, once again, we have 4 limit statements. And our top 2, once again, give us a whole. So we know we have a whole at -2. So we want x plus 2 in our numerator and denominator. And then our other limits both equal positive infinity, which give us our vertical asymptote at -1. And because both of those limits go to positive infinity, that means we need 2 of our x plus 1s in the denominator so that both of our sides of our asymptote are going the same direction. So we get f of x equals, we want our whole in our numerator and denominator. And then we have our vertical asymptote. So our last example, we are given a verbal description of the graph, of some of its properties, and we're being asked to sketch a picture of it. So for part A, we're told that we have a whole at x equals 1. So at x equals 1, we want to put a whole in our function. And then our next piece says as x approaches 4 from the left, f of x increases without bound. So this means we have a vertical asymptote at x equals 4. So we can go ahead, sketch that in, draw in our asymptote at 4. And then it says as we approach it from the left side, we increase, meaning we're going to be going up. So if we finish sketching the other side, remember it's eventually going to level out. And then at 1, we need to throw our hole in there. So we'll put a hole on our graph. And then the last piece of information says as we approach 4 from the right side, it decreases with outbound, meaning the right side of our vertical asymptote will be going down. So that is roughly what our function f could look like. And then I want you guys to try and sketch function g. So identify where your holes are and where your asymptotes are, and think about which direction it should be going. And I'll see you guys next time in class.